So section 8.2 is going to discuss a hypothesis test for a population proportion. Remember, all your hypothesis tests have to be about proportions, or actually parameters. So it'd be proportions, P, mu for means, sigma for standard deviations. In conducting this test, you're going to be testing claims like the majority of Americans think that the country is headed in the right direction. That's a claim about a population proportion. And we can test that claim, try and decide for ourselves if we think it's true or false, as long as certain assumptions are met. And these assumptions are, first of all, that we have observations from a simple random sample. That's going to be beyond the scope of this class to really test that, so it's just always going to be kind of assumed. But then we have the conditions for a binomial distribution are satisfied. Do you remember how to test whether or not something satisfies the conditions for a binomial distribution? It has to fit. Good. So fits. Fixed number of trials, independent trials, 2 samples, and same probability of success for all those samples. The last condition that we need to test is that the expected number of values, or expected number of successes, and expected number of failures are both greater than or equal to 5. So you might remember that mu equals n times p. That's your expected number of successes. So expected number of successes. And then n times q. Where does q come from? Does anyone remember? 1 minus p. So this is your expected number of failures. So that both of those expected values are greater than 5. If that's true, then we can get away with the approximations and the hypothesis test that we're going to do here. Now, these hypothesis tests are broken down into 6 different steps. And the reason for that is because I'm going to keep these steps the same for all kinds of different hypothesis tests throughout this course. When we test goodness of fit, test hypothesis for standard deviation, or 2 population proportions, or 1 sample mean. All kinds of different things are going to have this same flow. So hopefully this will get you into that flow. You're going to start by stating the null and alternative hypothesis. Decide on the significance level. That's alpha. What are our typical values for alpha? Thank you. So 0.05 and 0.01. If it's outside of that, boy, you better have a good reason for that. A lot of people are going to look at you kind of funny if you're using a value for alpha other than those. Not that you can't, it's just unusual. Now, with a classical approach, you would then use that value of alpha to find the critical values. Depending if you have a left tail, 2-tail, or right tail test, that's going to separate the z distribution, which is here, here, and here. It's going to separate your z distribution into reject and fail to reject regions. Then what you would do is calculate a test statistic. Here's the form of our test statistic. We'll do this by hand once, and then we're going to rely on technology after that. But based on the value of your test statistic, where it lands is going to tell you what your decision is. Are you going to reject H0, or are you going to fail to reject H0? Alternatively, after this first example, we can do this based on a p-value. So if our p-value is low, and by low I mean less than alpha, then you're going to reject H0. Do you remember what we said the other day in terms of making decisions? If the p-value is low, make me look good. HO must go. Excellent. Thank you. So that means you're going to reject if the p-value is less than alpha. That's going to be probably a more convenient way to proceed, but StatDisk gives you enough output that it's really not going to be hard either way. And finally, we're going to have to state your conclusion in words. And I'll give this to you. In fact, did I pass this out yet? No? Okay, let me pass it around. So there's a couple here, and then let me just pass it around there. Okay, so when you get this, I want you to do two things. In the upper left-hand corner, I want you to write your name. And the upper right-hand corner, I want you to write Jeff Parent is awesome. All right. Well, I'll tell you what. If that's there, what I'll do is I'll let you use this sheet on every exam. Okay? Fair enough? All right. No, I'm kidding. You don't have to write that, although it is nice. No, you don't have to write this. I will let you use these sheets on the exams. All right? So just do me a favor and keep these sheets clean from everything else. Don't write other notes on it. But if you keep these sheets clean, then I'll let you use them on the exam, and it'll help you with step number 6, which is going to be really important. That's going to be how you word your conclusion. We're using a lot of technology for this, so because we're not doing as much by hand anymore, we're relying on computers, I'm going to put a little more emphasis on step 6, which is stating your conclusion in words. Please stay away from the word prove. In statistics, we don't prove anything. That's reserved for a math course. Okay. So we'll start with problem number 6, which is kind of half done for us. They've got some output here for us. Okay. In a T connectivity survey of 1,000 adults, 29% said they would feel comfortable in a self-driving vehicle. The accompanying StatCrunch display results from testing the claim that more than 1/4 of adults feel comfortable in a self-driving vehicle. So let's take a look at that. Here's our claim. More than 1/4 of adults feel comfortable in a self-driving vehicle. I find that high. I don't know. How many of y'all think that it's okay to be in a self-driving vehicle? You guys ready for that? So 1 out of about 28, 29, 2, 3. All right, so that's like 10%. Yeah. I think I talked about my friend who was driving in a Tesla, the lane assist, and he just kept on staring at me. And after a while, I'm like, okay, you're showing off. Just put your eyes back on the road. And that was with somebody who was actually at the wheel. Self-driving vehicle? Not yet. All right, but this is the claim that you're testing. That's our original claim, and we're gonna have to be conscious of that as we do these things. So that's our original claim. More than 1/4 of adults feel comfortable in a self-driving vehicle. So let's start writing a few things down. This is problem number 6. P is greater than 1/4. You can also write that as P is greater than 0.25. Might not be a bad idea to write it that way because eventually we're going to need to plug that into Statistic or something like that. Now, let's first check some assumptions. And the first one I want to look at is simple random sample. Well, I don't know where these people collected their data, so we're just going to have to go with the flow and assume that that's a simple random sample. But the next thing I need to check is that this data fits a binomial distribution. So the first part was F, which is a fixed number, right? Well, we have 1,000 people in our survey. Are they independent? Yeah, if somebody feels comfortable or not with a self-driving vehicle, their attitude is not going to be influencing yours if you're selected at random. So, yes. Remind me, what's the T stand for? 2 outcomes. You're either comfortable or not comfortable. That's it. So just 2 outcomes, that's good. And S. Yeah, there was the same probability of success throughout your sample. Now, you actually get that based on the 5% rule, because your sample size is presumably less than 5% of whatever population you're trying to target. Now, it could be drivers in Michigan, could be drivers in the United States, but 5%, our 5% rule, I also liken it to the 20 times rule. If you multiply this by 20, it's 20,000. So 1,000 would be, 5% of a sample size, 20,000. Most populations that I could think of that I would want to apply this to are going to be bigger than 20,000. Number of drivers in southeastern Michigan, in the Midwest, United States, So by the 5% rule, even though we don't really have independent events, we really get both of these two. So we're good on those two assumptions. So the last thing then is to check n times p and n times q. Want to make sure that they're greater than 0.5. So that's going to be 1,000 times 0.25, which is going to be 250, and 1,000 times 0.75 is going to be 750. So the number of expected successes and failures based on whether or not we think that the eventual null hypothesis is going to be true are both greater than 5. So we're okay there. Okay. A lot of grunt work here before we start to actually get to our null hypothesis. I'm not going to take as much time doing this for future problems. Let's get down to the null and alternative hypothesis. This was the original claim. So let me circle that. That's our original claim. Sometimes I call it the orange claim, just for fun. Is this part of the null or alternative hypothesis? Alternative hypothesis, good. So HO and HA. P is greater than 0.25. Edry, what would the null hypothesis have to be then? Perfect. P is less than or equal to 0.25. Cool. Now, the problem is pretty much going to have to tell you what alpha is, or you're going to have to assume a typical value. So, in our case, let's see. Well, let's just use alpha as 5%. And that brings us down to the third step in this process. Third step, I've kind of given you a hybrid of instructions for that third step because I've kind of got my feet in both worlds. You've got a classical approach, which is define the critical values, and we've got a different approach, which is to do things based on a p-value. But let's go with the classical approach first, and that is find some critical values. Now, the critical values are going to come from a z distribution, but what tail test are we going to use for that z distribution? Well, we've got p is greater than 0.25. Yeah, it's going to be a right tail test. All right, so a right tail test. So draw our little distribution here. Z is in the middle at 0. A right tail test, 5% of the area is going to go in the right tail. And I believe we just did this one previous to me starting the video. you're going to have to be able to find for yourself z sub 0.05. That's going to be the point with 5% of the area in the right tail or 95% to the left. You can do that with the inverse norm on your graphing calculator, or we can do it with Statistic and normal probability underneath the analysis menu. Probability distribution, normal distribution, and area to the left is going to be 0.95. So area to the left, and there we go, 1.64485, call it 1.645. So 1.645. That's going to separate a couple things for us. You're going to have your reject H0 region and your fail to reject H0. So depending on our Z statistic, it's going to be in one of those two places. Now we can actually calculate the value of Z, which is our test statistic. It's going to help us decide, do we believe it or do we not believe it? And that calculation is given to you right here. You're going to take p hat, which is your sample estimate, minus p sub 0. P sub 0 is going to come from your null hypothesis. So Z equals p hat. That's the proportion of people in our sample that think it's okay to drive with a self-driving car. Just to remind you, that was 29%. So that's your p hat. So 0.29 minus 0.25, that 0.25 comes from your null hypothesis, divided by the square root of P0 is 0.25. If P0 is 0.25, what do you think Q0 is? 0.75 divided by your sample size, which was 1,000. So if I'm stuck doing this by hand, which makes those silly assumptions that, well, if you're on a desert island and you have to do it by hand. But let me show you how it would look on the calculator. I'd put parentheses here, 0.29 minus 0.25 divided by square root of 0.25 times 0.75 divided by 1,000. And you get about 2.921. So about 2.921. So that's looking at it old school, but that's your test statistic. If you actually looked at the problem, guess what? Test statistic, exactly the same. 2.9211, etc. Okay, so good. Your instructor can calculate with a calculator. Good for him. But the big thing is, what does that mean? What's your decision? And that's step 5. What are we going to decide to do with our null hypothesis? Where does 2.92 land in our rejection region or in the fail to reject region? Yeah, that's going to be right in here, right? 2.92 doesn't matter exactly where. 2.92 says reject H0. That's your decision. Now, step 6 in these types of hypothesis tests is always going to be the same. That is, write your conclusion in words. Now, I want this in words that somebody who hasn't taken a stat class can understand. And that's why I gave you a handout that tells you how to word the hypothesis conclusion. So, here's how you word things. And let me label this kind of this way. A, B, C, and D. You've got 4 choices for how you word your conclusion. But those choices are going to be motivated by the form of your alternative hypothesis. So, or excuse me, you're motivated by the choice of your original claim. So, let's go back up to the top here. This was our original claim, that more than a quarter of people are ready for self-driving cars. Okay. Does this claim contain the condition of equality? No. There's no equal to here. It's not a greater than or equal to, a less than or equal to, or an equal to. It's just not there. So, does the claim contain the condition of equality? No. Did we reject H naught? Yes. So, this is how you'd word your conclusion. The sample data support the claim that. And now you got to word the the alternative hypothesis in words. No longer good enough to say, oh, well, P is greater than a quarter. So, as a last step, step 6, let's write our conclusion in words. So, step 6, sample data support the claim that, well, more than a quarter of people, more than, let me put 25% of people feel comfortable with a self-driving car. Yay. That's it for that one. How's that look? You okay with that conclusion? Now this is going to get a lot easier because of a couple things. One, we're not necessarily going to have to look up this information, nor are we going to have to calculate this. So it's going to get a lot easier. I would disagree with that. Looking up the z-value, you mean this one right here? That tells you to reject or fail to reject. Now, this is a classical approach to doing your hypothesis test. This is set up these reject and fail to reject regions. But you're right, we're not necessarily going to do it that way. So, but for our purposes, with what we've done, yeah, you needed this value. Now, there's a different approach to doing a hypothesis test, and that's the p-value approach. Before I go to the p-value approach, are we okay with what we've got here? Yes, please.
Did you use C for the wording?
Yes. Yes, we use C. Okay. So the general flow of things in a classical approach is state your null and alternative hypothesis, decide on alpha, set up a critical region, and for that you're going to need to look up a test statistic of the critical value here. Calculate your test statistic, decide to reject or fail to reject, and then state your conclusion in words. P-value is going to make that a lot easier. What did I say about a p-value? How does a p-value help us out? What do we do? Yeah. If the p-value is low, H0 must go, right? So if the p-value is less than 0.05, then guess what? Then reject. Let's look at how nice that this becomes if you've got a p-value. Take a look at your output. The p-value is given to us, right? It's 0.0017. Is that less than 0.05? Cool. So basically, we could have skipped step 3 and 4 and said, okay, well, I got my p-value. I guess step 4 kind of gets replaced by the p-value as 0.0017. So that's our p-value. But since that's less than 0.05, you still get the same conclusion. You reject H0. And then you state your conclusion in words as before. But the p-value is nice because it's going to simplify things for us. We're not going to have to work as hard. All right, let's try another couple kind of from the ground up. Not necessarily working with an example that's been half done for us. At least you've seen the classical approach. I'm not really going to use that much, but you've seen it, and if you have to follow along with somebody else doing it, then hopefully that'll be okay for you. Any last wrap-up on problem number 6 here? TJ? P-value, and that was given to us in the book.
So if I wanted to find that on Statistic, given all the other information,
It'll be there. In fact, we're going to do it with Statistic. This next problem number 26. We're going to do it, and we'll get exactly the p-value and be able to make our conclusion from there. Okay. Let's take a look at let's see, problem 26. And let you read that for a second. Okay, so we're going to test the effectiveness of the nicotine patch. So, in a study of smokers who tried to quit smoking with nicotine patch therapy, 39 were smoking 1 year after the treatment, and 32 were not smoking 1 year after the treatment based on data from the study. Use a 5% significance level, so we're going to need that, to test the claim that among smokers who try to quit with nicotine patch therapy, the majority are smoking 1 year after the treatment. Let's write that part down and see if we can't make some sense out of it. The majority are smoking after 1 year. We need to turn that into a statement that we're going to use in our alternative or null hypothesis. So the majority is really talking about a proportion. So what statement involving proportions is this making? Perfect. P is greater than 0.5. That's your original claim. So let's turn that into a null and alternative hypothesis. Give yourself some room here because there's some other stuff I'm going to write down. Let's do HO and HA, and we'll also write down alpha. Let's go through HO and HA. See if you can't write down HO and HA. What do you think? Perfect. So the alternative is that P is greater than 0.5. The null hypothesis is that P is at most 0.5. Alpha is 0.05. That was given. Now, before I really get going, before I forget things, I should probably check a few things. Let's start with this. X is 39. That's our, and let me put quotes here, successes, right? I mean, I'm not sure we're really cheering for people to keep smoking, but that's what we're going to define as our success in this case. How many people are there in our study altogether? 71. Good. It was the 39 who were still smoking and the 32 who quit. That gives us a total of 71. Before I really do this, I should run through my little checklist. Simple random sample, that it fits, and that n times p and n times q are both greater than or equal to 5. Well, that's going to be 0.5 times 71, so that's like 35.5. So NP and NQ are both going to be greater than or equal to 5. So we're good there. All this does, in terms of checking our assumptions, is say that, okay, yeah, this test is appropriate. If it failed these, then you'd have to do something else. And that something else is not something we're going to cover until the very end of this course. We're going to do some non-parametric stuff. Okay, so we're going to do the p-value approach. We're going to need to enter some data. That's our step here. You can do this on a graphing calculator, or you can do it on Statistic. I'm going to show you on Statistic first. So we'll go to analysis. Where do you think I should go from here? What are we doing right now? Hypothesis testing. Yes. So hypothesis testing, and oh, look, proportion one sample. How special. Now, the first thing we need to set is the form of the alternative hypothesis. What does the alternative hypothesis look like? You've got three choices. Not equal to, greater than, or less than. Which one of these should I click for problem 26? Greater than. So if you look back at our alternative hypothesis, we've got P is greater than 0.5. So we're good there. And now we're going to type in everything else. Significance level, 0.05. We got that. Claimed proportion. Claimed proportion comes from your null hypothesis. It's 0.5. Our sample size was 71 people in this study. And the number of successes is perversely defined as those 39 people who didn't quit smoking. Click evaluate here. We get all kinds of great information. Let's see if we can't figure out what all this great information is telling us. There's really one number here that I'm going to focus my attention on. Can someone tell me what that number is? P-value right here. 0.20306. So that's really step 4 here for us, is to find that p-value. Now, if you fail to adjust the alternative hypothesis correctly, it's going to give you the wrong p-value. So if I had less than, oops, it's going to give me the wrong p-value. If I have a, not equal to, again, I'm getting the wrong p-value. So it's important that you adjust the p or the alternative hypothesis correctly. So p-value 0.2036, or excuse me, p equals 0.20306. That helps us out for the next part. We need to decide what we think about the null hypothesis. Should we fail to reject it or reject it? What are you going to do? Decide and then talk to a neighbor real quick. Tell your neighbor what you think. See if you guys agree. Okay. Kyle, what do you think? What are we going to do here? Is he right? Fail to reject? Excellent. Fail to reject. And I'd be happiest if you put in fail to reject H naught, because sometimes people fail to reject HA, which is wrong. So make sure you put in fail to reject H naught or reject H naught. If you just leave it at reject, it might be a little uncomfortable. Are we okay with this decision here? Yes?
How did you determine that 39 was the X, the success?
So that's going back to the problem. And naturally, I closed my book. Hang on, let me get to it. So, smokers who tried to quit with patch theory, 39 were smoking after 1 year. So that's the ones that are still smoking after 1 year. So those are the
No change.
yeah they didn't quit. Yeah, like I said, it's kind of a perverse definition of success.
Right.
But,
Whatever the behavior was, there was no change, and so that's why that's success.
I guess it's because we're trying to decide the proportion of those who are smoking after 1 year. So that's why I called them the successes. Those are the ones that were smoking after 1 year. So those were, in some sense, the success. Okay. Remind me. Whoops. Wow, that's interesting. All right. Let's hope that I didn't kill the video here. There we go. Which one of these was my original claim? Good. HA. Now, it's important to decide which one's your original claim because that's going to help us determine how we word the conclusion. So, let's take a look here. Does the original claim contain the condition of equality? No. Did we reject it? No. So you're going to go down here. You're going to start out your conclusion with there's not sufficient sample evidence to support the claim that, and then you got to state it in words. So start out with what's prescribed. There is not sufficient sample evidence to support the claim that. And what is this in words? Good. That more than 50% of people are smoking 1 year after nicotine therapy, after the patch, after using the patch. That more than 50% of people are smoking after 1 year on the patch. Beautiful. But please make sure you say this in words. Don't use symbols. Don't use the greater than symbol. Don't use the less than or equal to symbol, etc. Make sure you state it in words. This is something that people should be able to read even if they don't have a stat background. How are we looking with that? It's a little bit better with the p-value as opposed to going through all that other stuff with the critical values. It's not that hard, given the output with Statistic, to actually do it with a critical value approach, because they give you, first of all, the test statistic, and then they give you the critical value. So you could easily do this with Statistic. In fact, it makes it even easier for you. I don't even have to draw this. Check this out. You hit the plot key. There you go. So here's your, let's see. Let me just take a quick look at this. The critical value is 1.64485. We've seen that a couple times. And this test statistic falls in the fail to reject region. So fail to reject. So it's pretty easy if you're doing it either way. It does seem a little odd, even though we had 39 out of 71 people that said, okay, they're smoking after 1 year, but that's not enough evidence. But remember, you got to do this beyond a reasonable doubt. And we didn't actually make that level. If you had a bigger sample size, it probably would have been okay. But our sample size wasn't enough, didn't give us enough oomph to put us over that threshold of rejecting. So that's what's going on with this one. All right. Yeah, because we ended up with like 55% of people who quit. So it was like a little disappointing. But it wasn't enough evidence, probably because we didn't have enough big enough sample size. In fact, here, just a little test here. If I made this 710 and this would be 390, I'll bet you that changes. Now look at your p-value. There you go. A lot smaller. You'd reject in this case. And it's still the same proportions. It's just you have a bigger sample size. So that was the problem with that first study here. Anything else on problem number 26? Okay. Let's try another one. Problem number 24. In a study of checkout scanners, or store checkout scanners, 1,234 items were checked for pricing accuracy. 20 checked items were found to be overcharges. If you want to undercharge me, hey, no problem. If you want to overcharge me, there's an issue. So 20 of them were found to be overcharges, and 1,214 checked items were not overcharges. Use a 5% significance level to test the claim that with scanners, 1% of sales are overcharges. So, okay, that's your original claim right there. 1% of sales are overcharges. Okay, let's take a look at that. Problem 24. P is 0.01. That's 1% of sales are overcharges. Let's check our assumptions. We don't really know how the data are collected, so we're just going to assume a simple random sample. Let's see if the data fits. Fixed number of trials, yeah, 1,234. Independence, well, independence and same probability are both going to come to us because of the 5% rule. So we can take care of those twos. And there's two outcomes, right? You're either overcharged or it's not an overcharge. That's it. Those are your two outcomes. So it fits. M times P is going to be 1234 times 0.01. Should be able to do that in our heads, right? Multiplied by 0.01 is just going to move the decimal 2 places to the left. So 12.34. And hey, that's greater than 5. So we're good there. What's Q going to be? Yeah, 1 minus that, so 0.99. So it's going to be this minus this, so it's going to be 1221.66. And again, that's greater than 5. So both of our assumptions are, all three of our assumptions are going to be satisfied, provided that it was a simple random sample. So 1% of sales are overcharges. That's what we need to test. So, okay, let's put that in here and test away. Start by stating your null and alternative hypothesis. We're going to test this at the 5% level. Try and write down HO and HA for us. Okay, Rachel, what would HO and HA be, please? All right, P equals 0.01. What about HA? Perfect. So it's either equal or not equal. So we're in good shape there. Thank you. Alpha is 0.05. Next, I guess we need is some statistics that we're going to input into Statistic. N equals 1234. What's the number of successes that we had amongst those 1234? How many people or how many items were overcharges? 20. All right, so we'll input that. Now, you can do that in Statistic, but I promised to show you how to do this on the graphing calculator, so let me show you how to do it on the graphing calculator. So, let's see. Stat, and then go over to test. We want a 1 proportion T test, or a 1 proportion Z test. So it's the 5th option down from the stat menu, and then test. I'll select that. Now this is going to be 0.01. Number of successes was 20 out of 1234. And then you got to type in or figure out, well, what's the alternative hypothesis? It's either P is greater than some number, less than some number, or not equal to some number. In our case, it's the not equal to, but you know, that can change depending on the problem. And then I'm just going to simply ask the calculator to calculate this. And what's the one number that I need here? The p-value. You got to be careful because it's giving you kind of two things here, right? It's giving you p hat, so that's the actual proportion, and then it's giving you the p-value. So the p-value is 0.0284. So that's kind of like my fourth step with the p-value. P equals 0.0284. And again, you're faced with a decision. Accept H0 or reject H0. Give that a little thinking. See what you think. William, what do you think? Reject H naught or fail to reject H naught? Which one? You got a 50-50 shot. Give it a shot. Fails? Do we agree? Fail to reject H naught? I'm not seeing anyone rushing to your defense. I'm sorry. Yeah. So if the p-value is low, H naught must go. Right? So is this less than alpha? Yes. So that means we're going to get rid of the null hypothesis. We're going to reject it. So reject H naught. If this was bigger than alpha, then you'd fail to reject H naught. It's just that simple. Okay. Are we all right with our decision here? Let's see what that means for our conclusion. Which one of these was our original claim, my so-called orange claim? Good. Right there, that's our original claim. So we need to know that in order to decide what form of the conclusion we want to use. Does the original claim contain the condition of equality? Yes. Did we reject? Yes. So we're going to use A. There is sufficient sample evidence to warrant rejection of the claim that sufficient sample evidence to warrant rejection of the claim that. Now we got to state what this is in words. Perfect. 1% of sales with scanners are overcharges. Thanks, Jasmine. Okay, I'm hoping you're starting to get into this routine a little bit of all these 6 steps. When I ask you to do hypothesis tests on the exam, I'll lay out your answers so that you can put in all these 6 steps, and then I'll grade you appropriately. I want to see parameters here, so like P or mu or sigma, those things. Calculating your test statistic. I want to see your p-value. I'm going to see your decision here, and then I'll read your conclusion. Now, a lot of times you might have this wrong, but that's because this is wrong. So I might take off some points for that. But if you answer this consistently, then I'll give you some points here. So make sure you get this part right here. Are we good with problem number 24? Sure. Okay. All right. So yeah. So the first step is to adjust the alternative hypothesis. So I think sounds like that's where you made your little kerfuffle. Yeah. And then the rest of this, 1234, and let's do 20. Okay. Let's take a look at the graph. So our test statistic is in blue, and notice that it's in the rejection region, right? So at least doing this, the classical approach is giving us the same conclusion that we got by doing the p-value approach. With our p-value approach, since p was less than 0.05, then we said, okay, let's reject. With the classical approach would be setting things up like these, like one of these. In fact, we did this distribution here, but we still fell in the tail, so again, it said to reject. There is one thing about this one that bothers me, and I haven't completely reconciled it yet, but it's something we're going to pay attention to moving forward. Let me go back to the results. They give me a confidence interval here. What do you think about this confidence interval bothers me? The confidence interval is where we think the true population parameter lies. So it's somewhere between 0.00916 and 0.02325. Well, what's wrong with that in light of our conclusion? Yeah, 0.01 is actually in this interval. So there's a little something more that I got to figure out exactly why this is going on. I'm not exactly comfortable with this just yet, but I will get back to you with this. The p-value, our confidence interval conclusion should match what we see based on our p-value and the classical approach, this plot. Those should all be saying the same thing. If they don't, there's a little problem. So I owe you some more explanation on that, and I will get back to you on that. Okay, it's Halloween. Let's do a candy example, right? Yay. I think problem number 12 is suitable for that. Yeah. At least this one won't involve any calories on our part. At least not yet. Is M&M's anyone's favorite candy? No. Far from it. Almond Joy? Okay. Anyone? How about Reese's? Anyone else? Reese's? Man, my kids bring Reese's home. I'm like, what you got? I'll be grabbing them. All right. So, let me see if I can get that a little bit better focus. There. Dataset 27 contains weights of 100 M&Ms. 27% of them are blue. Now, they're not exactly giving you X, but they certainly give you a way to figure out X, right? What's 0.27 times 100? What's 0.27, right? So 27% of them are blue, so great. The M&M Mars company or candy company claims that the percentage of blue M&Ms is equal to 24%. Use a 5% significance level to test claims. To test that claim. Let's stop there. We'll go back and answer this last part after we do our hypothesis test. But I want you to kind of lead the way on this one. Where should I start? Come on, there's a chance we can get out early. Let's go. Chop, chop. All right, claim or the assumptions, both of them are good. So let's start by writing down the claim first. What's the claim that we're going to test? Perfect. P is equal to 0.24. So the claim is that the percentage of blue M&Ms, this one, there we go. Percentage of blue M&Ms is equal to 24%. So P equals 0.24. That's our claim. So let's write that down. Then we can work on our assumptions. And I'm not sure if it's the fact that we're doing a video or not, but I've never been so good about doing the assumptions. I really am not. I'm terrible about doing those things. Simple random sample. We're just going to have to hope that that's true. Fits. Does it fit? Fixed number of trials? 100. Independent. If you grab one M&M at random, is its color going to depend on, another M&M? No. So, two outcomes, blue or not blue, same probability of success. Yes. So we're good there. N times P and N times Q. 100 times what? 0.24, good. Because that's our hypothesized value. That's the one we want to use. So if P is 0.24, what's Q going to equal? 0.76. And both of these are greater than 5. We don't actually need to do the arithmetic, although we could do it quite simply. But both of them are greater than 0.5 or 5, so we're good there. Now let's get down to our steps. You can continue to lead the charge, though. Help me out with our first step. Thank you. HO is at P equals 0.24. Good. Good. Thank you. Now let's not make Jasmine do all the work. All right. So we got the first two. Now what do I do? All right. Step 3. What are we gonna do now? All right. So we're gonna need to input some data. Our sample size was what? 100. How many successes did we have in those 100? How many of them were blue? Yeah, 0.27 times 100, or 27. Cool. That information either goes into Statistic or into your calculator. Either way, you should be able to come up with things. Let's do it in Statistic. So let's see, claim proportion, that has to change. That's 0.24. Sample size is 100. Number of successes was 27. Of course, that's more than the 24 that we expect, but is it enough more that we can say, yeah, you know, I don't think M&M's is really right when they say 24%. What number do I need out of this? What's the p-value? So p-value is, let's see, wait a minute. Do I have this adjusted right? Yes. Okay. That's a mighty big p-value. All right. So the p-value is 0.482. Step 5 is up to you. You need to make a decision. So make your decision. Check your decision with your favorite neighbor. And at the same time, decide what you're going to do for your conclusion. Which one of those forms we're going to use to state our conclusion. Sure. Okay. Aj, what'd you decide in step 5 based on our p-value? Fail to reject. Do we agree with that? Fail to reject? Good. Fail to reject H0. Michael, we failed to reject. We got to decide which one of these are going to be the basis for our conclusion, wording our final conclusion in words. What was our original claim? Good. That's our original claim. Sometimes the orange claim, right? Let's see. So let's work our way through this. Does the original claim contain the condition of equality? Yes. Did we reject the original claim? No. So we should be using B. There's not sufficient evidence to warrant rejection of the claim that. How would we state that in words? What is this in words? There is not sufficient evidence to warrant rejection of the claim. Here's where you're in your money. So far, all this is kind of given to you. What should I write in words? Yeah. The 24% of M&Ms are blue. That 24% of M&Ms are blue. Are we okay with that conclusion? Let's take one look back at Statistic. Take a look at your confidence interval. What important number is actually in that confidence interval? 24. 24%. Our confidence interval includes 24%, but we didn't reject H0. Those go together, right? Because if we're saying, all right, well, we can't prove that M&Ms, 24% of M&Ms aren't blue, then our confidence interval should contain 24%, and it does. It's comfortably inside that confidence interval. So, any last-minute thoughts or questions on hypothesis testing here? Okay. For homework, try problems 1 through 27 should be pretty good. You can skip problems 29 and 31. Cool. All right. Have a good one. See ya.